Welcome. Today let us begin by looking at the changes in enthalpy and entropy of 1 mole of a pure substance in a closed system in terms of changes in temperature and pressure. As you are comfortable by now, temperature and pressure are easily measurable, and we are going to look at changes in enthalpy and entropy as a function of the changes in temperature and pressure. To do that, let us write enthalpy as a function of temperature and pressure, and also entropy as a function of temperature and pressure. Again, by now you should be comfortable with this. The total differential dH in enthalpy is equal to dou H dou T at constant P. Remember, we had taken this as a function of temperature and pressure. So, dou H dou T at constant P times dt plus dou H dou P at constant T times dP, and we can write a similar expression for entropy also. The differential of entropy, total differential, ds equals dou S dou T at constant P dt plus dou S dou P at constant T dP. By now you might begin getting ideas as to how to handle these partial differentials. Using the earlier equations, I have given you the numbers here. You can go back and check what these equations are, but as we present, it should come back to you. We can write dH as Cp dt. Recall that we are replacing dou H dou T at constant P. Dou H dou T at constant P is nothing but specific heat at constant pressure, and also note the term for this, dou H dou P at constant T. So, dH is Cp dt plus, as we had seen earlier, dou H at dou P at constant T can be written as V minus T dou V dou T at constant P. This is what comes from equation 237 that you can go back and verify. Let us call this equation 248. If we use equation 238, you can again go back and check, but it is going to be quite evident here. This V minus T dou V dou T at constant P, this is nothing but a part of the definition of alpha, the expansivity. Expansivity was 1 by V dou T at constant P, and therefore you could replace this with V minus alpha V T, and if you take V common out, you will get V into 1 minus alpha T times dP, and of course the Cp dt remains here, which equals a total differential. Let us call this equation 249. Now, okay, look at the thing here. We have enthalpy, the variation in enthalpy, the total variation in enthalpy as expressed as Cp in terms of, that is Cp V alpha and T. So, this is easily computable. Similarly, let us consider ds equals dou S dou T at constant P dP dt plus dou S dou P at constant T dP. Again, as you may recall, or if you want, you can go back and check equations 235 and 236. We are essentially going to replace these partial differentials in terms of the more easily measurable variables. We have already seen that dou S dou P was Cp by T as given by equation 235, and that is what we have substituted here. Therefore, ds becomes equal to Cp dt by T, and we have seen through equation 236 that dou S dou P at constant T could be written as minus dou V dou T at constant P. So, that is what we have substituted here. Therefore, we get ds equals Cp dt by T minus dou V dou T at constant P times dP. We will call this equation 250, which can be expressed as, we are going to use equation 238 now, ds equals Cp dt minus alpha V dP. Note that this is dV dou V dou T at constant P. Therefore, this is variation of volume with temperature at constant pressure, expansivity related to expansivity, and therefore, this is nothing, the 1 by V is actually the expansivity, and therefore, this becomes alpha times V. We will call that equation 251. Now, that we have the expressions for the variations in enthalpy and entropy of 1 mole of a pure substance in terms of Tp and other easily measurable variables. We will look at an exercise where we can get more comfortable with the use of those equations. As earlier, I am going to present the exercise, then I will give you some time, maybe 10 minutes, to work things out, think through it, first think through it. There is a whole aspect of problem solving. If we have time, we will get into that a little later. We first need to think about the problem, see what is given, what is required, how do you relate what is given to what is required, and then work out what is required. It is simple to say, but it is not very easy in practice unless somebody has a lot of experience or is very good. Let us get to this exercise. A high pressure water vessel is being designed for a bioprocess plant. It needs to take water that is available at 27 degrees C and 1 bar to 47 degrees C and 30 bar for coupled generation, energy generation purposes, and further use inside the plant. This is a very typical scenario. Calculate the change per mole in enthalpy and entropy for this process, the values of which will help in the first level design. We are at the design stage now. The average values of useful properties that can be used are Cp equals 75.3 joules per mole per Kelvin, specific volume or molar volume is 18.2 centimeter cube per mole. This is a nice number to remember, this is for water H2O, 18.2 centimeter cube per mole. Alpha is 5.05 into 10 power minus 4 Kelvin. Please go ahead, take about 10 minutes and work this out, and then I will present a part of the solution. Now, let us look at how to go about solving this. I am just going to give you a hint, and then I am going to give you another 10 to 15 minutes to work things out. Maybe you should take 15 minutes to figure out how to go about this. If we integrate 249, I hope you recall, I can go back and check what 249 is. dH equals Cp dt plus V into 1 minus alpha times T dP. If we integrate this, yeah, that is the equation there, we will get delta H here, and this is straightforward integration. Cp dt, therefore it is Cp average T2 minus T1. We have taken Cp average because Cp is a function of temperature, that you may recall from the earlier classes in thermodynamics. Therefore, strictly speaking, we must express Cp as a function of temperature and then integrate this. Nevertheless, for small changes in temperature, taking Cp to be a constant is not a big error, does not result in a big error. Therefore, we take an average value of Cp between the two temperatures of interest. Here there is only a 20-degree change, and we should be fine. Here if you integrate this, this is molar volume, we will again take this to be a constant, it may not be a bad assumption, times 1 minus alpha average T average dP is P2 minus P1. Now why do not you substitute the various values to get delta H? Since there are some calculations involved, why do not you take about 15 minutes. Okay, let us go forward. Substituting the values that were given, check the units first, make sure that the units are consistent. In this case you do not have to worry about it, all the values are given in consistent SI units. So it is 75.3 Cp average, T2 expressed as Kelvin, remember that expressed as Kelvin, 320 minus 300. In this case it does not make a difference because we are taking the difference. So whether you take it as in centigrade or in Kelvin, it does not make a difference, but it is good to take it in Kelvin where appropriate. And the molar volume, the average value was given 18.2 into 10 power minus 6, alpha average was given 5.05 into 10 power minus 4, here it is 1 minus that into the average temperature of 320 and 300, which is 310, and the pressures in the consistent units were 30 and 1. So 30 minus 1 into 10 power minus 5 to get it in the consistent set of units. So the first set of values would come down to 1506, the second set of values would come to 44.25. It is good to note the relative contributions of these terms. Cp average T2 minus T1 is 1506, whereas V into 1 minus alpha T P2 minus P1 is only 44.25. It is good to keep noting these relative contributions to be able to make quick estimates which are also reasonably close to what we require. In this case, since we have calculated both, we need to calculate both here. This is not too small either, it is 44 out of 1500, and therefore it is good to take this. So 1506 plus 44.25, 1550.25 joule per mole. This is delta H. Now why do not you go ahead with the integration of 251, go back into your notes and integrate 251, see what you get, this is for delta S, see what you get in terms of the measurable properties, substitute the values and find out what delta S is for this particular case. Take another maybe 10 minutes, since you know the scheme now, why don't you take about 10 minutes to find out. Okay, let us go ahead with the solution. Integration of equation 251, if you recall, it was Cp dt by T minus alpha V dP. Therefore, delta S would be, you have a dt by T term there along with a Cp, and therefore if we take the Cp average value here, Cp average times ln of T2 by T1, integral of dt by T is ln T, and therefore you have, when you substitute the limits, you get ln T2 minus ln T1 or ln T2 by T1. Here this is straightforward, minus alpha average V average into P2 minus P1. Substituting the values, now we know the values, we get 75.3 into ln of T2 320, T1 300 minus 5.05 into 10 power minus 4 into, this is alpha, this is molar volume V 18.2 into 10 power minus 6, and this is 30 minus 1 conversion into the proper system of units, we multiply by 10 power minus 5 and 4.89 minus 0.027. It is also nice to note the relative contribution of the values. Here you get 4.863 joule per mole per Kelvin for delta S. Take it on face value now that these are useful values for the design of the process itself. You would have some idea as to how these come in useful for process related aspects from earlier classes. Maybe we will see some related aspects in the later part of this module itself.